my faculty didn't make it very clear, and it needed a very long time to understand what is going on. So there are extensive variables, and the S over here, and they tell us how big is the system. And there are intensive variables, where it is kind of unfortunate that one of them at least, or two of them, we can feel, temperature and pressure, because that gives us a certain notion what temperature and pressure might be. But really, they are just the price. They're just the price in energy for the system to obtain more entropy, to obtain more volume, or to obtain more material. So yes, it also happens that temperature is telling us how warm it is, but it is really the price the system needs to pay for energy. And the negative pressure is really something which pushes on you, but it's really just the price the system needs to pay for volume in terms of energy. And then the chemical potential is just the same kind of thing. It's the price the system needs to pay to put in additional quantities into it. So it is all very symmetric in a way set up here. And yes, then volume and temperature and pressure and so also have other physical meanings, and we're going to talk about them quite at length and how we relate them to atomic properties. But that is really ancillary in this kind of question. Okay. And then we said, okay, let's think about something. Let's think about what is so startling about suffering, and why can it work, and how does it have to do with this equation. So, clearly, your cell phone has internal energy, everything has. And in your cell phone, there's a battery which powers your cell phone, you all know that, and it also has an internal energy. And that can change by changing the temperature, and your cell phone might get a little bit warm, but you all know your cell phone doesn't derive really its power from getting warm. So the temperature change of your cell phone is probably not so important. Pressure is certainly not important for your cell phone. It's not to charge it by pushing on it or something like that. So it has to do with the chemical potential. That's the only thing left. So it has to do with the chemical potential. And now we all know that a cell phone works with electricity. And so electricity, then the chemical potential, what's relevant in electricity? Probably electrons. Could be ions, but in a way it's probably electrons. And in any way it's closely related. They are both charged particles. So what we're really dealing with, how this battery can power the cell phone, is the chemical potential for electrons. And the difference in chemical potential for electrons on this side of the battery and on that side. So if I have a difference of chemical potential for electrons here and for chemical potential for electrons over here, then the internal energy is given by how many electrons I have here, n, number of electrons, times the chemical potential. So then on this side here, if I put so and so many electrons on this side and so and so many on that side, the n having this way or that way, on the left and on the right, then if I shift the mouse, I can release energy, the energy which powers your cell phone, which makes the screen come on live, which allows it to connect to the internet and so on and so forth. So it's all the chemical potential which really powers your cell phone. It's the difference in chemical potential for electrons on this side of electrons. So batteries are important, and I hope on Friday I'll get to bring you some examples, something. But batteries are really a linchpin in us making progress economically and technologically in telephone. And it has to do with electric cars are nothing new. Replacing a horse with an electrical motor and a battery is more than 100 years old, and making it carry it electrical. there were in the beginning of cars more electrical cars than with internal combustion engine. It is really old technology, but it never really worked because people didn't understand the chemistry, they didn't optimize the chemistry. So what in physical chemistry is done is understanding how to make the chemistry of batteries so that they can actually help us. And that can be for making cars work or not work, as shown over here, or making planes work or not work, as was shown in this article, and makes for your cell phone to work or not to work, as you experience as your cell phone ages. What usually dies first is the battery of that cell phone. And it is just as important for the power grid in California, if you can store solar energy from the day for the night, or things like that. Batteries are tremendously important. Batteries are a key subject of research these days, both in academia and in industry, and so understanding batteries is important. So we just realized batteries have to do with electrons, and we also know Chem 1 electrons are sitting in states right here, this one on the left hand side. And then molecular orbital theory, I just taught Chem 1 last quarter, Chem 1A. I was teaching molecular orbital theory saying, oh, if I have two atoms now and they form a bond, then I have out of the, say, the two hydrogen atoms, out of the 1s states, I'll get the sigma 1s bonding, the sigma star 1s antibonding orbital out of them. I get two orbitals. And that's where the electrons are sitting. Chemical potential, what's the chemical potential here? Chemical potential is in some way the energy, correct? How much energy does it cost to fill an electron in here and here, and more energy is released when I put it here than when I put it there, correct? So the energy in the molecular orbital diagram is also a chemical potential. So if I then have three, I usually teach how ozone is set in Chem 1A. Not all my colleagues do, but ozone, you have bonding orbital, an unbonding orbital, and a non-bonding orbital, because you have three atoms interacting with each other, and this gives then rise to the delocalized electrons in ozone. So you have three orbitals that way, three atoms. So that's how ozone will go. And then you can go further on and say, oh, four, nothing comes to my mind right now, but six would be benzene, for instance. Then you go more and more, and here you have 30 or so, and now they come closer and closer, more and more orbitals. If I have a solid block of metal here, like a solid block of metal over here on the left hand, this piece of metal, then there are, of course, a gazillion of atoms in there, 10 to the 23rd or more. And so we'll get 10 to the 23rd or more orbitals over here, where the atoms can sit. Oops. Everything okay? Okay. And then the electrons will find that they want to have the most favorable chemical potential, the electric states with the lowest energy, that's where they populate. And then at some point, all the electrons occupy, we'll have fountain orbital, and then we'll get some empty states as well. And that brings us to the difference between a metal, a semiconductor, and an insulator. I think you learned that in school, grade school. But metals are objects where those orbitals, which we just looked at, those orbitals which come out of molecular orbital theory, where those orbitals are, the largest one of them is either not completely filled, it's only partially filled, like shown here, or where I have two different bonding systems, maybe the sigma and the pi bonding system, and they kind of overlap so that one isn't completely empty and the other one isn't completely filled in this way either. So that at this level where the highest energy electron is located inside this object, at the chemical potential of the highest energy electron over here, that there is an infinitesimal interval higher energy still in available state. That is what describes matter. And then we have semiconductors. In semiconductors, it is that there is a HOMO, the highest occupied molecular orbital, and a LUMO, a lowest unoccupied molecular orbital. And these are delocalized, and these are orbitals which have many, many states in them, many, many states like those ones over here, many, many states. But there is a gap between them where there are no states. And these ones are the filled, the occupied ones. And these ones are the empty, the unoccupied ones, the LUMO. And then there is a gap in between here, and the gap corresponds in energy to something which I can populate just by having room temperature in the semiconductor. And then there are insulators, and they just work the same way as the semiconductors, just the gap is larger so that I can need higher temperatures, or not really temperatures, practical anymore, to move electrons from the bottom to the top. There is no strict borderline between the semiconductor and the insulator. You'll find some values here or there in books, but don't trust them. It really depends on what you want from the material, what you call them. People are calling diamond a wide bandgap semiconductor. It's an insulator for all practical purposes, but it really depends on, oh, am I wanting to use it for electronic application? I call it a wide bandgap semiconductor. Do I want to have it for other applications? I call it an insulator. It's it really has to do whether they are practically semiconductors or not, whether the bandgap is commensurate with thermal occupation or not. Now, what are typical band gaps? 1 electron volt, 2 electron volts is already wider band gap semiconductor. 3 electron volts, probably an insulator. 4 electron volts, an insulator as well. Somewhere there. You are good edition, you all know what an electron volt is, I hope by now. It is a very, very useful measure of energy, something which I will learn in this class a lot. If you were with me in Chem 1A, you would have had to memorize the ionization energy of hydrogen, 13.6 electron volts. As the only other electron volt values. Electron volts are handy because they are very close, 1, 2, 3, 4 in reasonable regimes. So make sure you know it. Now, if I look at these ones here, then I can make a line over here in the middle, correct? I can make this line, which is just the borderline between occupied and non-occupied. This line here has many different names. You can say this line here, that's the chemical potential of electrons in this material. Because if I add electrons or remove electrons from the material, that is the energy on average I gain or need to pay. For the metal it's easy because the states are very close to each other over here, so it doesn't really make a difference whether how much energy it is putting in and taking out. For the semiconductor, it's not quite as easy. If I want to take an electron out, I need to take it from the filled state. If I want to put one in, I can only put it to the empty state. So there is a difference in energy, and then the chemical potential is the average. The average exchange rate of electrons with the material. That's the chemical potential. And here for the insulator, that difference is of course larger, but still the average of the two, that is the chemical potential for electrons. Now, if you particularly talk about electrons, you often don't call it chemical potential, you call the whole thing over here the Fermi energy. It's the name for the chemical potential for electrons, it's called Fermi. But it is just the chemical potential for electrons. The other complication in that regard is that if you come from a physics perspective, you refer every unit to a Coulomb, 10 to the 19th electrons. If you're a chemist, you refer everything to a mole of electrons, 10 to the 23rd electrons. And so there's a conversion, a constant between them, which is called the Faraday constant, which is about 100,000, which relates the Coulomb and the mole to each other. How to avoid any problems? Easy thing, electron volts. Electron volts is per electron necessarily, and so per electron it doesn't make a difference whether you think about moles or coulombs, but we really only think about what are. Okay, then, yeah, we had that. Now, if I have an electron vacuum, my Chem 1A students were very astonished about that, but you all know that. If you have an electron vacuum, would it rather be with an atom, or even if the atom is neutral or not? Of course, it would rather be with the atom, because you can polarize the atom, and then the polar nature of the polarized atom will bind that extra electron, and so you have an electron affinity of atoms which is non-zero, they bind electrons. So the energy of an electron in vacuum is way, way up there. And then the energy for electrons in a medium, in an insulator, semiconductor, metal is shown over here. The difference between those two is very frequently abbreviated in the Greek letter phi over here and has this very descriptive name, work function. Yes, it has nothing to do with work, and it's not really a function, but it's called the work function. The work function of a material is how much energy it costs to take the electrons out of the material and put them in vacuum. So now we have three words which are closely related. Chemical potential. Chemical potential for electrons would be this value here, referred to a mole of electrons. Fermi energy would be this energy here, either referred to a coulomb or more commonly just per electron in terms of electron volts. And then work function here is this difference. The work function is always a positive number. So even though it goes down in energy, people write that down as a positive number, just like one energy people write down as positive numbers, of course. It's actually energy we produce. So there is one of those many problems with having the sign of the numbers in electrochemistry, and we'll get to this really more in this class. Okay. So this is a slide from Chem 1A, at least she took it with me. I'm showing over here the electron affinity, and I'm showing the ionization energy. Here's the ionization energy, here is the electron affinity, and what you see over here is, first of all, the difference in numbers. These go to like 2,000, and this one goes like to 200. So the ionization energies are much higher, costs more energy to take an electron out than is released when you put an electron in. Not astonishing, because the atoms are like insulators. If you take an electron out, you need to take it from here. If you put an electron in, you put it over the out there. Difference in energy. And if you take the average between them in an appropriate way, you get the chemical potential for electrons of your atom. And they're different. Look at the different material. Helium over here has a very high ionization energy, and down here electron affinity is pretty low for that. And then you can go to other, like potassium over here has a fairly low ionization energy, and then you have somewhere here, pretty high. Okay. The bottom line, what I really want to say over here is the electron, the binding of electrons is different between the elements. That should not really be news to you. You are all chemists and you know that different atoms behave in different ways, and so the binding energy of electrons should be different to all of them. But it's also sometimes easy to So let's assume I don't have a coin with me right now, but I have a penny and a nickel. Penny being copper, the nickel being, okay, nickel not so, but of course shine. If I put them together, what will happen? The astonishing thing, at least it was astonishing to me when I looked at it, is that if I put the penny and the nickel to each other, then I have the electrons in the zinc or nickel over here, and the electrons in the copper over here. Then what will happen is that just by putting them together like this one over here, I will have electrons in the zinc which have much higher energy over here. Lower binding energy, higher total energy, lower work function of zinc, higher work function of copper. Those electrons here in the zinc will say, I don't stay up here. I will go over there. I can lose energy. Energy can be released if I go over there. Or for practicality, they happen to go over here, and then there's no way to go for them to go back anymore. And so in the end, we have a flux. So if I just put two pieces of metal to each other, two dissimilar pieces of metal to each other, I will have charge transfer between them. I will have electron transfer. I don't need an outlet, I don't need a battery, I don't need anything special in order to transfer electrons from one object to another. I just need to put them together with a zinc copper. If I put zinc and copper to each other, I have the electrons from the zinc run over to the copper. When will it stop? Chemical potential. When will things stop? When the chemical potentials are in equilibrium, right? So, you really have a stability condition which we have to look at here. We have to, again, think about our chemical potential. Ever had a multimeter you had, a voltmeter with a dial over here and two prongs? So, you can measure the voltage. You stick it in the outlet and it says 110 volts or 20 volts. And you stick it to a battery like in the lab and you find how many volts come out. If you were to do that over here, it's actually a homework question, but I give away the answer. If you were to measure the voltage between the copper and the zinc with your two prongs, your two terminals of your multimeter, you would measure exactly zero. Why would you measure exactly zero? Because it's clear that electrons moved over here. There's a charge in the copper compared to the zinc. Why on earth would the difference with what you measure with the multimeter be zero? The reason for that is that's the chemistry over here. We are creating equilibrium. As soon as we have equilibrium in the electrons between the zinc and the copper, meaning the Fermi level of the zinc is now in equilibrium with the Fermi level of the copper because we have a space charge on one side compared to the other, then there is no driving force for electrons to go this way around or that way around to our voltmeter. And if there's no driving force for electrons to go to our voltmeter, the voltmeter will say 0 volts. Because putting two metals to each other creates contact potential. It creates a voltage in some way, but it doesn't drive electrons in some way. It actually is a process of creating equilibrium. So if I were able to measure the voltage, if I had like a compass needle which can send not magnetic field but electrical field, I could see the voltage difference between them if I placed them. But if I just put my prongs over there, I will not see them. It's just on potential. It's a reference on the equilibrium. Okay. So we come back over here to this. Come to this one, right? That's really the relevant point. If I put my two metals to each other, the volume won't change, entropy won't change, pressure won't change, temperature won't change. They all are irrelevant. It's about this part on the right. It's about the equilibrium. It's about chemical potential. And then we can come to stability equations. And I want to do those things next time. I'm going to go on a little bit more about batteries and what they are practical for, and then we start writing things down. Batteries until 25 years ago, and in cars, even these days, you can still buy a car with a lead-acid battery. Lead is PV, down there in the periodic table here, heavy element. Is it smart if you want to transport a battery around with you to make it out of brass? Really? Probably not. Especially if you want to use it for some transport application, you need to lug around that heavy battery in your car or in your plane or whatever the transport application is. That's also the reason why when I was a child, there were no cell phones. Because there was just no battery you would want to lug around. And then as I grew up, first those cell phones came about where you had the suitcase in one hand for the battery and the handset. And now cell phones are different. And that is because people realized, oh, let's go up in the periodic table, make the batteries lighter. And now they're there. That's where batteries. Batteries are now working with lithium. And so let's talk a little bit for the rest of the day about the kind of battery you have in your cell phone. So you want to make your battery light. In the periodic table you want to be up. And you want to make your battery so that there is lots of charge which can be stored in little volume, because you want to have it both light and small, the battery. So I need to find an ion which is really small. This seems a good choice, isn't it? So, lithium-ion battery. So, the lithium-ion battery in your cell phone works relatively straightforward. It has two materials in it, two electrodes. We call them electrodes, those two materials. And one electrode, and most of the things which you have these days is made out of graphite. Graphite, you know, the sheets of carbon. If you call the individual sheets, you call graphene. The whole thing you call graphite. Maybe you also call it coal. That's the same thing. So if you have graphite, then you have those sp2 bonded layers of carbon over here. And if you are a metal atom, then you say, oh, I like being a graphite. It's almost as good as being a metal in the first place. I have lots of nearest neighbors, lots of nearest carbon atoms, which all have those high clouds of electrons surrounding them. A metal feels really comfortable with it. So if I have lithium, lithium feels pretty comfortable over here in the graphite, sitting between the layers of the carbon, doing its metallic bonding with those high delocalized clouds of electrons. So I can store lithium inside a graphite electron. But if lithium wants to be here, it needs to be neutral. There's no counter ion in the graphite. There's nothing negatively charged in the graphite, so I can only have neutral lithium in there. So for the lithium to be able to intercalate itself in the graphite, it needs to be neutral lithium, lithium 0. That is one electrode. The other electrode is made from cobalt oxide. Cobalt oxide, CO, cobalt O2, is the formal charge of cobalt is clearly +4. Our oxidant is -2 formal charge. So I can make just a cobalt oxide electrode over here. Cobalt oxide has the advantage that it is a fairly good conducting oxide. Now, if cobalt oxide says lithium, then the cobalt says, oh great, lithium, help me form this oxide. I can be to my favorable oxidation state +3, and the lithium takes 1+, and it's still O2, and each of the oxygens has a 2-. So cobalt oxide can become lithium cobalt oxide just by having the cobalt be reduced by 1 charge, having lithium 1+, and otherwise having exactly the same structure. There's next to no structural transition. So lithium can sit in the cobalt oxide as lithium cobalt oxide. Now it's lithium plus. Or lithium can sit in the graphite as neutral lithium. And that is how our battery in the cell phone works. Because it is more favorable for the lithium to go over here and help the cobalt form the cobalt oxide by making lithium cobalt oxide. And it is good but not so favorable for the lithium to sit over here. So, when the battery discharges, that means the lithium is dissolved in an electrolyte from sitting not anymore in the graphite, but now swimming in the electrolyte as a lithium plus ion, and then traveling over to the cobalt oxide electrode where it makes lithium cobalt oxide. But in order to do so, it needs to give up one electron. It needs to be lithium plus, so that the oxidation states work out. So there's an extra electron. And because cobalt oxide is a conductor, or at least reasonably conducting oxide, I have now an extra negative charge on this side. This becomes the negative pole of my battery. This is the negative terminal of my battery. This extra electron that the lithium needs to give up to form lithium cobalt oxide. And then I can run that through my cell phone to bring it back over here. And so this charge is that the lithium is traveling to the cobalt oxide. And then if you want to recharge your battery, you just apply voltage to the setup over here. You apply a negative voltage to the side. You have lots of electrons over here. Lots of electrons means that sometimes the lithium get neutralized by those lots of electrons which are available over there, and then can travel to the other side. So we have this setup for the battery. Now, if you're a real physical chemist, you would never like to have such a display as for Popular Mechanics or whatever. I took that actually from the website of the manufacturer of the lithium batteries. That is clearly made for the public display. Because if you're a physical chemist, you want to look at this way. You always look at it this way. As physical chemists, when you draw a battery, you always draw it so that the oxidation takes place on the left-hand side, the lithium becomes lithium plus, and the reduction takes place, the cobalt becomes from 4 plus to 3 plus, takes place on the right-hand side. So you always do it the other way. That is a really important convention. If you forget about this convention, then all the voltages will turn around, and that's not good, because then we make lots of mistakes in figuring out which will happen spontaneously and so on. So, as physical chemistry, always we want to have it drawn up like this. Now, what I really need to tell you, teach you in this class, is not a lithium battery, lithium-ion battery. Yes, we barely know anything else. But what you find on subject GRE tests and what you find in chemistry textbook is typically a Daniell cell. Has also to do with telecommunication. The telegraph, this newfangled device in the 1850s or so, which allowed you to put Morse code signals over miles and miles to the next relay station over the wire. That one then operated with a Daniell cell, and so being up to date and modern, I need to teach you the Daniell cell. I really have to, because you might be asked about this thing later on in some contexts, and so we really have to study the Daniell cell. But of course, the Daniell cell is completely non-ground. But maybe it's a nice display of what can go on. So it's simpler in a way, it's even more symmetric. The Daniell cell has a zinc electron and a copper electron. And the zinc electrode and copper electrode, they each sit in an electrolyte. An electrolyte is something where charged particles can move in. They can be dissolved. Light, LYT, means it is being dissolved. And electrode, something which is charged. Okay, an electrolyte here, an electrolyte there. Now, we already looked at copper and zinc earlier and found that the work function of copper is greater than the work function of zinc, meaning that electrons are stronger bound to copper than they are bound to zinc. So it is favorable for more of the copper ions here in this electrolyte to become
copper atoms and strongly binding electrons, and more and more of the zinc on this side to get dissolved because they bound the electrons only weakly. And then the electrons can travel through the wire, through the load, which might be your car, yourself, from your telegraph, whatever you want to apply over there, and from one side to the other. So really we are looking at a redox reaction, right? We are looking at copper 2 plus zinc makes zinc 2 plus copper. The only thing which separates an electrochemical reaction, which we are looking at over here, from a typical redox reaction is that in space we separate the location where the reduction and where the oxidation takes place. Here we have the oxidation take place, there we have the reduction take place. Rather than getting a big flame because we put it all together, the energy is lost on the load on this wire attached to the terminals which contact the electrodes, which then sit in the electrode. So there we have many words: terminal, electrolyte, electrode, the load, and then the whole cell thing is called a galvanic cell. Galvanic cell is just another word for battery. Oxidation takes place on one side, reduction on the other. We always write electrochemical cells so that the oxidation is on the left-hand side. We always do. You always do, please. Reduction is on the right-hand side. The whole cell thing is a cell. This is a half cell. This is the other half cell. Two half cells together make a whole cell. Then we have to talk about anode and cathode. These are also important. They were really easy to teach 20 years ago because at that point people had TV sets which were cathode ray tubes, those old style TVs with a long vacuum tube from the back to the front. In the back you had electrons being emitted and then the electrons were accelerated and were impinging on the screen on the front against the phosphor which makes a certain color. And that is the cathode ray tube because at the back of it there is a cathode where the electrons are emitted. So cathodes are where electrons are emitted. Here we have the cathode on the copper side because the electrons are emitted from the copper electrode into the copper 2 plus ions into the solution for them to become copper. And then the opposite to a cathode is an anode, and the anode is where electrons enter the material. The zinc dissolves a zinc 2 plus, leaving the electrons in the electrode over there. So in a way, electrons go into the electrode. Hence, this thing is an anode. This is a galvanic cell, and the opposite of that is an electrolytic cell. An electrolytic cell is a cell in which electricity is used to dissolve something. Electricity is used. Lytic, something is dissolved. It's an electrolytic cell. So this Daniel cell can also be an electrolytic cell in some way or another. Maybe not really, but we're going to talk about it. But it's an electrolytic cell in the sense that if I apply a voltage now to this copper, if I apply a really high positive voltage to the copper over here, then the copper would probably say, okay, I can reduce my positive voltage, I can reduce my shortage of electrons in this electrolyte by putting some copper ions into the solution as copper 2 plus, leaving some electrons on the electrolyte electrode, reducing my shortage, reducing the positive voltage. And the same thing, the negative side, if I apply negative voltage over here, then if I make really high negative voltage, then that means there is so much a surplus of electrons over here that some of those electrons can go into zinc 2 plus ions in the solution, making them neutral zinc, trading them on the side. Opposite direction. But see, the voltages, they still stay the same. Minus side is here, plus side is there. Minus side is here, plus side is there. And now you see that I made a mistake making those lights. This, of course, has to be the short bar, and this has to be the long bar. The long bar is really the plus side, the short bar is really short, as I'm saying. So my apologies for that, please correct me. Okay, so we have that. I think then I can only leave you with the homework. Homework is, I told you already, the first part of the homework is, can you measure that contact potential with a normal multimeter? And describe why not. There is do some sentences. Think about why you cannot measure that contact potential with a multimeter. And then the second question is, figure out how big the mole and the coulomb are, and how they incompatible, and how huge amount of energy you can get from a mole of electrons. That's really important. And find for that huge amount of energy some everyday ways of calculating it. Enough to run the dishwasher or something. Okay, with that, thanks so much.